Limits. This is the first video in the business calculus series. Let's take a minute to discuss what calculus actually is. What is calculus? It's the study of how things change. And as you know, in the world, nothing ever seems to be stationary for very long. Things are changing this way and that. And calculus helps us quantify and describe those changes, and it helps us study things that change. Now, since everything changes, it seems like calculus is going to be good for everything. And that's true. Okay? The main idea behind calculus, the first idea, is a thing called a derivative. Maybe you've heard about it before, maybe not. The thing about the derivative is it's defined as a limit. So before we can really sink our teeth into the calculus and start to describe the instantaneous change that we'll call the derivative, we must first understand the concept of a limit. So this video is the introduction to limits. Okay, so let's get started. Here I've written the basic thing that you're going to see when you're working on limit problems. It says lim, and then it's x, right arrow to a, f of x. And how you're going to read this is the limit of f of x as x approaches a. Keep in mind that in this context, a is a number. It's a real number, just like all values of x are when we put them into the function f of x, okay? The key idea that we're going to learn here in limits, the key idea is that the value of x is very, very close to that number a, but x does not exactly equal a when we are taking the limit as x approaches a. That's the key. I've underlined it in red here, and I'll show you what I mean by an example. Okay, so let's take a look at a familiar function. Maybe f of x is equal to x squared. Hopefully by now you know a lot about this function. For example, it's a quadratic, it's a polynomial, its domain is all real numbers. And one of the most important things that I hope that you continue to practice is graphing the function and getting a picture. A picture is always worth 1,000 numerical values. So there you go. That's a nice picture of the parabola known as x squared. Okay, so let's think about taking a limit here. What if I wanted to consider what is the limit of the function f of x that I just drew as x approaches the number 2? Okay, so this is going to be how the function f of x behaves as x gets very, very close to the number 2, but is not actually equal to the number 2. Okay, so here's 2, and what is f of 2? That's 4, that's right, because if I plug the 2 in there, then it tells me to square it, so I get up to here, so I get to the point 2 comma 4, which is to say that f of 2 is equal to 4, right? Okay, so as x approaches the number 2, which is to say it's very, very close, maybe over here, maybe x is equal to 1.9999, or maybe over here, really close on the other side, x is equal to 2.000001, something like that. For values very, very close to the number 2 for x, what kind of values are we going to get when we put these into the function? Well, we'll get different numbers depending on what number we put in, but if we plug in numbers that are close to 2, we're going to get out a number that's very, very close to 4. That's the concept of a limit. It's like, what is your function doing as x sneaks up to this one specific point? So that means that the limit of f of x as x approaches to here is going to be 4. Okay? The reason the answer is 4 is because the output of the function is approaching the value 4 as the input of the function is approaching the value 2. Alright? And it just so happens that f of 2 is equal to 4, which is to say that the limit as x approaches 2 of f of x happens to equal f of 2. Okay, this is a special property that we'll discuss later. It's called continuity, when the function's value is equal to the limit as x approaches that point. So for now, let's just say that this is nice. It makes me happy when it turns out that the limit is equal to the function value at that point. Okay, so now let's contrast this with a slightly different function. I'll just change it a little bit. I'm going to stick with this parabolic form, but I'm going to change the function definition. I'm now going to say, new function, let's call it g of x. I'm going to define it piecewise. So this is some pre-calculus knowledge. You guys remember how piecewise functions are defined? starts with a curly bracket on the side here. And for this piecewise function, I'm going to say it's equal to x squared as long as x is not equal to 2. But when x is equal to 2, I'm going to say it's equal to 3. Okay, so I personally just defined this function where, this should be going like this, like a hole like there, okay? And then a little dot, just like that. Okay, so here's the number 3. Okay, so this is a graph of the new function. It's a little bit different. It's piecewise defined, where we have the parabola going on as long as x is not equal to 2. But when x is equal to 2, I actually want the function to be equal to 3. Okay, so let's consider the limit. But before we do that, just a quick check of your pre-calculus knowledge. What is g of 2? What is g of 3? I just want to make sure you guys understand how to get the output values in a piecewise defined function. Okay, so try those out. Well, let's see, g of 2, I have to go to the instruction list over here, and it says whenever x is equal to 2, that's the input, you will spit out a 3. Okay, so that answer is 3. What is g of 3? Well, if the number is not equal to 2, then you're going to take the number and square it, and that's exactly what I'll do, and I'll get 9. Okay, so those are some of the important, those are just some of the function values there. But now the new concept is the limit. So let's consider the limit as x approaches 2 of g of x, okay? So now that I'm focusing in our attention onto the value x equals 2, I'm just going to get rid of this. That was just for an example. What do you think the limit is as x gets very, very close to 2, but keep in mind, x does not equal 2. Okay, when I talk about this limit, I'm not talking about x equals 2. I'm talking about every value that I can think of for x that's extremely close to the number 2, but it is not equal to the 2. And for those values, how is the output of the function behaving? Like if I plug in the number 2.000001, what number will I get as an output? What number will be very close to? 4, right? That's where that hole lies. But if I plug in any number that's around 2, then the function output is actually approaching this value of 4, as it was before. Turns out the limit's equal to 4. Okay, that's the tricky thing about limits. You cannot just take this value for the a here as the input and just plug it into the function. Because you see, g of 2 is not equal to 4. It's equal to 3 by the piecewise definition. However, the concept of limit is that the values of x are going to get very, very close to 2, but not equal to, and the output is very, very close to what? Looks like it's still approaching 4, so it's still very, very close to 4. Okay? So that's just our very beginnings of limits, and let's go into a picture example now and kind of just test your understanding. Oh, sorry, before we get into the picture, I want to give you a couple more concepts. What I was doing here is called the overall limit, and let me break down for you what is called the one-sided limit. This is another concept you're going to need. Okay, so there's actually two one-sided limits because we're working on the real line here, which has two directions. It's got that way and it's got that way. Alright, so we're going to have two types of one-sided limit. It's going to be called the limit from the left and the limit from the right. Okay, and these one-sided limits tell us which way are we approaching the value a from. Like this one is going to be written as the limit as x approaches a, but it says from the left, right? This is the left side here. So it seems like if I'm approaching the value a from the left side, then I'm going to be a number that's less than a. And that's why you put the little minus sign there. Okay, now likewise, if I'm going to take the limit from the right, here's the right side over here. It looks like if I'm going to consider values on the right, those values will be greater than the number. So I'll put a little plus sign because they're just a little bit bigger. Okay, so these are the two one-sided limits. And we can go into another example and show you how you take those limits. All right. So for this example here, I'm not even going to give you the analytical form of the function. I'm just going to draw a picture. And for this picture, to really illustrate the limits from both sides here, I'm going to say, let's say I'm approaching the number 4, and maybe my function looks like this, but it's not equal to that at 4, and then it goes like this, and then it goes down like that. Okay, so I'm going to be interested to see what are the limits as I sneak up on the x value of 4. And remember, when I put the a there, that's like the limiting value. That's the value of x that I'm sneaking up on. Okay, so let's say that this height right here is 2, and let's say this height up here is 5. Okay, so before I say anything else, I'm going to ask you for these one-sided limits. Maybe you want to try it out yourself. Okay, so I'll just write this on the board. What is the limit of this function? Let's call it f of x. The limit of f of x as x approaches 4 from the minus side. And what is the limit as x approaches 4 from the plus side? Okay, what the one-sided limits are asking for is what is the behavior of the output of the function itself as the input number sneaks up on this specific number either from the left or from the right. Go ahead, take a guess. Okay, so let's see what's going on. If I'm going to approach 4 from the left, that means I'm a number less than 4, so maybe I'm a number like this, 3.9999999. And if I input a number like this, my output is coming up here, right? And as I get closer and closer and closer to the input of 4, what is the height of the output getting closer and closer to? 2. That's right. So the answer's 2. Okay? Let's do the other one. And if you didn't already do the other one, why don't you take a guess now that you've seen this one? What do you think that answer is going to be? Now I'm going to sneak up on it from the right, so maybe I'm like 4.00001. Very, very close to 4, and just slightly larger than it for this one-sided limit from the right. Okay, if I plug in a number like that, you can see that my height will be up here. And as I get closer and closer and closer to the number 4 from the right, the height is approaching 5. Right, so the limit from the right of f of x as x approaches 4 is going to be 5. Check that out. Those are the one-sided limits. But when I started talking to you, I was first introducing limits by asking what is the limit. This is what's called the overall limit over here. And the overall limit, what do you think it is? Well, I haven't told you enough yet. One thing you want to compare between the one-sided limits and the overall limit is that the overall limit exists only if the limit as x approaches a from the left is equal to the limit as x approaches a from the right. The overall limit is the limit that I started the lecture with. Notice on the overall limit here, there's no plus and there's no minus sign. So which one do I mean? What I really mean when I'm asking for an overall limit like this is I mean from both sides at once. And you saw in the previous examples that it turned out that whether I approached it from the left or I approached it from the right, I was going towards the same place. And that's why that limit existed. Okay, that's before I told you this, and now you understand it more deeply, that I need to have both of these one-sided limits be equal to the same value. And if they are equal to the same value, then that's the value of the overall limit. However, if they are not equal to the same value and they don't match here, then when I approach it from here, it's 2. When I approach it from here, it's 5. What can I say about that? All I can say is DNE, and that's actually the right answer. Does not exist. That's what the DNE stands for. You're going to start to see that a lot. The limit does not exist if the two one-sided limits do not match. Okay? So let's do a couple more examples now, and I'll draw you a picture, and I'll ask you for some one-sided limits and some overall limits. And keep in mind that you really want to do the one-sided limits first for each point. And if the one-sided limits match, then the overall limit will exist. Okay, let's get a nice picture of a function here. Maybe it goes like this. Okay, and then let's get some points. Maybe this is -1. This is 0, of course, that's 1. Let's call this 2. Call this 3. Call this 4. And this is 1. This is 3. Okay, and maybe that's minus 1. Alright, so now I've drawn a pretty funky function. I'm not going to give you an analytical expression, like an equation for this function or anything, but I am going to start asking you for what are some of the limits, okay? So let's break it down. What is the limit as x approaches minus 1 from the plus side? Let's call this function f of x. What is the limit as x approaches minus 1 from the minus side? What is the overall limit as x approaches minus 1? There's 3 questions on this board here in part A, and they're all about x approaching the value minus 1. And I'll put up some similar questions for some other points and see how much of this you can fill in just by looking at the picture. X approaches 1 from the minus side. X approaches plus side, and the overall limit as x approaches 1. And we'll just ask it one more time, maybe for the point 3. When you're doing problems like this on a quiz or test, I have to emphasize that you really want to look at the statement of the limit very, very carefully. As you're going to see on these examples, the answers vary whether I have a little minus sign up there, a little plus sign up there, or whether I don't have it at all. This is the overall limit. Which one am I asking? And the numbers are going to change possibly depending on which one. Okay, so make sure that you look very carefully at the point A that it's approaching and from which direction if it is a one-sided limit. Alright, so go ahead and pause the video and try to fill in all of these mysterious questions. Did you get it? Alright, let's change to a different color, see if you got it right. Let's see how we're trying to figure this out. The very first question is, what is the limit as x approaches minus 1 from the positive direction? Okay, so that means from the right, okay? So I'm going to sneak up on the number x equals minus 1 from over here. Now, what number is the function approaching as the input x approaches minus 1? What number is that? 0, right? That's an intercept. That's an x-intercept. That's right. So the answer is 0 for that. And likewise, what I'm doing over here is I'm sneaking up for my input on x from the minus direction. So maybe I'm like minus 1.1, maybe I'm minus 1.001. And again, I'm approaching the x-intercept, which is 0. And now we're going to use the knowledge that we just learned, which is that if the two one-sided limits match, that's then what we conclude for the overall limit is the same thing. Okay, and that kind of makes sense, and it actually turns out nicely enough. It turns out that for this function right here, f of minus 1 is equal to 0. Okay, so it turns out that the limit of f of x as x approaches minus 1 is equal to the function value f of minus 1. They're both equal to 0. Don't forget, when you're taking a limit, the x is getting very close to minus 1, but it is not equal to minus 1. That's a very important concept here. Okay? It turns out they match. Later, we'll call that continuous. Happy. I'm really happy if the function's limit matches its actual behavior. That's nice. Okay, so did you get these ones? Now I switched it up a little bit. Here I approached one from the left instead of the right first. Okay, so now I'm going to sneak up on it like this. And what height is the function approaching? 1. That's right. So the answer is 1, not because the input is 1, but because the output, the function's height value, is 1 over there. And what about when I sneak up on the x equals number 1 from the positive side? So I'm just a tiny bit bigger than 1, and my output values are just getting closer and closer and closer to 3. That's right. So the answer is 3 here. And so if I asked you for the overall limit, and keep in mind that I could ask you for the overall limit without asking you for the one-sided limits first. It's up to you to understand that you have to evaluate both one-sided limits in order to conclude an answer for the overall limit. And what's the answer here? And these ones don't match. That's right, DNE does not exist. The answer is that that does not exist. Does that mean that f of 1 does not exist? Like if I actually plug in the number 1, what would my output be if I plug in the number 1? 3. Well, it's a filled in circle right there at 3, right? So the function value exists. The one-sided limits both exist. However, the overall limit does not exist. And that's unfortunate. This is going to be a point which we will call discontinuous a little bit later. Okay? Not continuous. The overall limit does not exist. All right, on to the last point. I hope you guys are doing well on this so far. So far, so good. We're going to sneak up on the number 3. And the height of the function is going down, down, down. And it looks like it's approaching -1. Likewise, if I'm going to sneak up on the number 3, down, 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 from the positive side, the height is still approaching -1, and whenever those things match, that's the overall limit. You got it. Okay, so each time you're asked for an overall limit, you're really taking both one-sided limits and seeing if they match. All right, what is the function's value when I plug in the input of 3? -1, that's right. Now, I purposefully drew a little sharp corner here. See if it would throw you off. Hopefully it didn't. It's okay. Even though it's a sharp corner, the function still exists there. Just like the function still exists here because it's a filled-in dot. Even though there's some weirdness here, what we'll call a jump discontinuity there, it's okay. The function still exists. So this is a point in which also it turns out that f of 3 is equal to -1. So I'm happy with that because the overall limit exists. The function value exists, they both match. We're going to call that continuous later, and that just gets me the happy face. Okay? So these are the kind of questions you should expect when I give you a picture and then ask you for all these limits. Hopefully you're getting more comfortable with that. And I'm going to end this introductory video with a little fact that we're going to use quite often, and it's pretty nice. It's a fact about the polynomials. Now, who remembers what a polynomial is from pre-calculus? Try to remember it right now by yourself. What is a polynomial? Polynomial. That was a function that we defined, f of x, let's say. And what it is it's a combination of a bunch of positive whole number powers of x, okay? So, for example, I could use x to the 0, and I could call the multiplicative number in front of it a0. Now, since any number to the 0 is 0, I'm actually just going to erase the x to the 0. But I start that way because the pattern is as follows. Your arbitrary polynomial is defined as all the positive integer powers, or I should say non-negative integer powers, of x with possibly a multiplicative constant in front. So each one of these a's is just a real number. They could be equal to 0. Hopefully you're good at recognizing polynomials now, because I'm about to give you a really nice fact. The fact is that the limit of x, as x approaches any number a, of f of x is always equal to the function value f of a when f of x is a polynomial. This is the beginnings of what they call the algebraic or analytical method of evaluating limits, which is to say that if I give you a polynomial function and then I ask you for the overall limit or even the one-sided limits, the answer is plug and chug, okay? So that's why you want to get good at recognizing the form of a polynomial. Go back to the pre-calculus lecture if you need a little refresher on that. And if you're ever asked for the limit of a polynomial, you just take the value of a, the input value that x is approaching, and you just toss it right in the function, and out comes the function value. That's the answer for the limit. It's also the answer for the one-sided limits, because the one-sided limits must have had to agree in order for this limit to exist. Okay? Polynomials are really nice functions, so they're always just going to be happy face for me, because it turns out they're everywhere continuous and they're really well behaved. Okay, so that's the introduction lecture, and in future lectures we'll talk about some of the more not so nice functions.